So today we are going to talk about capacitive sensing. So let's start with what is probably far too basic, but what a capacitor is, okay? So a capacitor is broadly defined as two conducting elements that are capable of holding opposing charges. Don't know why it's making that noise. Capable of separated by a medium. Right. So the classical capacitor that most of you have probably dealt with in your field theory classes and things like that would be simple parallel plate capacitor, like so. Let me try to draw these as if they were better connected. So we have two parallel plates. Let's define the positive polarity on top. So this will be V. And just for the sake of argument, let's call V a time varying voltage, and we'll get into that in a moment. So we would store some positive charge Q up here and some negative charge minus Q down here. And then our medium in between our plates, which is what I'm putting in pink right here, also has some influence on the behavior, where this is called the dielectric material. And it has some relative permeability. No, permittivity, sorry, I'm so used to talking in my magnetic circuits class where we're dealing about permeability all the time. I'm now getting it backwards. Epsilon is the permittivity, will be epsilon R times epsilon naught, where epsilon naught is the permittivity of free space, 8.854 times 10 to the minus 12 farads per meter. Okay. And the capacitance of this particular geometry, C, is equal to epsilon A divided by D, where the A is the cross-sectional area of the plate. And D here is the distance between our parallel plates. Okay. So buried inside this one expression, we can actually see that there are three different ways by which to change a capacitance, okay? So the most common way to implement a change in a capacitance is to have a structure where the value of D, the distance between the plates, can change. And that's largely what we're going to talk about today, okay? The second most common way to do it is to change A, the area of overlap between the plates. This is accomplished very often using what is called a capacitive comb drive structure, which I think we're going to talk about immediately after we get back, because the math that goes into it is a little bit more in detail. And then the last way that we could observe a change in capacitance or cause a change in capacitance would be to change epsilon, or specifically change the quantity epsilon R. So effectively, if we have some scheme by which we can change the material that's between the plates while holding the plates constant, we can also get a change in capacitance. That is used extraordinarily infrequently, and I can say that with a large degree of confidence because one of the projects that I did for my PhD dissertation was on effectively dielectric tuning, and there were about 3 other papers on it at the time that I did my dissertation. And the reason nobody does it is because it's very hard and very annoying. So anyway, all right. So in this class, we are going to focus largely on a change in distance, D causing a change in capacitance. Like I said, when we get back, we'll talk about changes in A, and then we're going to leave changes in epsilon effectively alone. Okay. So capacitance measurements are largely based on determining the amount of current flowing through a capacitor, where the current passing through a capacitor, I, as a function of time, is the derivative of C times V with respect to time. And this is actually going to give us 2 terms, okay? So we're going to have C dV by dt, which is the term that all of my circuit students are familiar with. That's our classical thing. The capacitance stays constant while the voltage changes and we get some current out. And then the thing that's probably a little bit new will be what happens if we hold the voltage constant. We'll have change in capacitance with respect to time, where this can be treated as our AC current as a function of time plus our motional current as a function of time. So in normal operation, one of these terms will be significantly larger than the other, okay? So the AC term is usually related to what we're going to call displacement measurements. And this is going to be low frequency measurements. So accelerometers and things like that, where we are not expecting to have a lot of events occurring in a small amount of time, right? And then for motional, these are going to be rate of change measurements. Typically at higher frequencies. And so this is when our capacitor is effectively undergoing periodic oscillations. So if we're dealing with vibrations as opposed to impulses. Okay. So let's start by looking at rate of change measurements. Okay. So if the voltage across a capacitor is kept constant, current flowing through the capacitor is approximately VDC times the change in capacitance with respect to time, or the motional current. For our parallel plate geometry, our motional current will be, again, VDC times the derivative of C with respect to time. And we can split that derivative up into a change in capacitance due to plate displacement, X, multiplied by the derivative of plate displacement with respect to time. So we're going to treat effectively everything but our displacement as a constant for our capacitor equation. So we're going to pull out epsilon. Over here, we're going to have A. And now we're taking the derivative of the capacitance with respect to the displacement, giving us a quantity of d minus x squared down here. And then we have our change in displacement with respect to time, which will be approximately our DC voltage epsilon A over d squared times our plate velocity. Okay. Or specifically, displacement's much, much smaller than our nominal gap. So let's put this equation into use. All right. So I'm going to draw a picture here. It's going to take me a couple of moments, so I apologize. So up here, I'm not remotely finished, but we'll talk about it in a second. I have a diaphragm. Okay. So effectively, it's just a large plate. And then let me explain what this thing is as I try to draw this other half of it. So this bit right here is a fixed lower plate with holes in it. The holes are going to allow air to pass through easily to limit the effects of air damping. And then encapsulating things here. Our diaphragm is acting as our upper plate. Okay. And it will move due to vibrations. So what this terrible picture is a MEMS microphone, like you have in your phone. All of our phones run on a device similar to this. Surface micro machined, excuse me, bulk micro machined device where we have a diaphragm that is oscillating above some electrode. So let's say that the area of our plate is 1,000 square microns. The nominal distance between our plates are 1 micron. We are going to have a vibration amplitude of 10 nanometers. This guy is biased with a 5-volt source, although in our phones it's more likely to be 3.3 volts nowadays. And our plate is oscillating at a frequency of 500 hertz. So somewhere in the ballpark of a B flat. Okay. What we want to figure out is the amplitude of our motional current. So what we learned a moment ago is that our motional current is given by VDC epsilon A divided by D minus X times X dot our velocity. And actually it should be D minus X squared if I'm remembering correctly. Let's scroll up here. Yeah. Okay. So which of these pieces of information do we know? Let's start there. We know VDC, we know D, we know X, and we know A. Really, yeah. So epsilon naught, let's write that down, is a constant. 8.854 times 10 to the minus 12 farads per meter. Right? So what Mr. Gordon suggested is we really just need to know the relative permittivity of the medium between the plates. So in most standard microphones, that medium is air, which has a relative permittivity of approximately 1. So if we know epsilon naught, we effectively know epsilon as well. So the only thing that we don't know is our plate velocity. Okay. So it's hard to say what the instantaneous velocity or anything is, but we can get a ballpark of the average velocity by simply thinking about what's happening, right? So when our plate is oscillating at a frequency of 500 hertz, we have something like this happening, right? So this is our plate displacement as a function of time, and here's time. So let's say that it starts off at a 0 position. Like so. Where this distance, the period of our oscillations, is exactly equal to the reciprocal of the linear frequency. Right? So it's the total amount of distance that our plate travels. Well, if our vibrations have an amplitude of 10 nanometers, I would argue that to go from here to here, our plate has traveled 10 nanometers. To go from here to here, our plate has traveled another 10 nanometers. From here to here is an additional 10 nanometers. And from here to here, in one cycle, it travels a total distance of about 40 nanometers. So we could say that it has an average velocity of the total distance the plate moves, 40 nanometers, divided by the time it took to move, which is the period. So effectively, we can guesstimate that our plate velocity is going to be 4 times the amplitude of our displacement times the frequency of the oscillations. From that, we have a pretty reasonable estimation of what our velocity is, right? Because there's no way for us to tell what its instantaneous velocity is without literally knowing that it's a sine wave and taking the derivative of said sine wave at different points, okay? So we're only concerning ourselves here with, for the most part, the amplitude, okay? So if we substitute in our numbers for all of these things, what we're going to get is 0.903 picoamperes. That is our amplitude of our motional current. Okay. Very, very small thing. If we instead use the approximation, right? Because our amplitude here, 10 nanometers, is pretty small as compared to our gap distance D of 1 micron, right? So it's 1/100th of it. I would consider X to be much smaller than D. Well, if we used our assumption, we would actually find that we would have 88 picoamperes. So that's still a considerable, or excuse me, 0.88 picoamperes, right? So 1/100th was enough to cause pretty reasonable change in our output current there from a perspective of estimating what's going on. So I personally am a bigger fan of using the more precise equation, unless we're talking on the change, excuse me, the a factor of 1,000 or more. All right, so this is an example of a rate of change measurement, okay? Now let's talk about a displacement measurement. So displacement measurements actually, before I do that, I just want to talk about something else just very, very quick here, okay? About these rate of change measurements. Okay, so we have a DC voltage that's biasing this thing. So if our sensor isn't undergoing any displacement, what is the amount of power that is consumed by our sensor? 0, right? So let me erase this and then we'll talk about it, right? So let's just say that we have a simple system we have a top plate biased at some voltage VDC. And then here is our capacitor. And then down here is ground, right? So if C is constant, I is 0. No power absorbed whatsoever. So we have no power draw. It's only when our sensor undergoes vibrations that our device actually consumes power. This is one of the benefits of capacitive sensing, is that only when we have something to causes a current to flow do we actually consume any power. So we typically use in very, very low power applications and all that kind of good stuff. Okay, we'll talk about how that compares to piezoelectric sensing, piezoresistive sensing, and all that kind of good stuff later. All right, so we're going to contrast that with displacement measurement. Where undergoing displacement measurement, our current I is C dV by dt. Really, all this implies is that our bias voltage will be an AC quantity. Okay. We're still going to have a change in capacitance, right? Because we're not trying to figure out how to measure a change in voltage. That's fairly straightforward. We're trying to sense something by observing a capacitance change. It's literally just the frequency is so low that we have to use an AC signal in order to actually pick up the change in capacitance, okay? So I'm going to draw another picture here, and this is going to be of a rather crappy accelerometer. And we'll talk about how we could make it better if we were so inclined later on. Okay. So I have an anchor point here. Let me draw my anchor point here. Let's give you guys some dimensions. So let's say that our plate in the middle here is square and has a dimension of L2. Our guided beam springs will have a dimension of L1, like so. They will be W in width. Let's say that our plate is made of 100 single crystalline silicon, such that E is equal to 130 gigapascals, And I'll write this up here because I didn't give myself enough room. Silicon has a density of 2,330 kilograms per meters cubed. So this is our top view. And then our side view is going to be something like this. So there's our anchor point. This is our dimension W for our springs. This is our spring thickness T1. And then here we have a big old plate thickness. T2. Down here is our electrode. So this is our nominal gap D. And then on this side, we just have another spring over here. So this is our side view. Okay. So let's say that this accelerometer experiences an acceleration of A is equal to 10 Gs in the Z direction. So we're expecting our plate to move downward, right? And we want to figure out a couple of different things. Okay. The biggest thing here is going to be the change in capacitance due to this experienced acceleration. And then from that, we are going to determine what are called a displacement sensitivity and an acceleration sensitivity. So let's see, I've given you the acceleration, I've given you the density of silicon, I've given you the Young's modulus of silicon. You've got the dimensions of the springs, the dimension of the plate. I've told you the distance. No, I've told you what it's defined as, but I haven't given you any of the dimensions. Okay, sorry. So let's say that our spring has the following dimensions. L1 is 200 microns. W is 20 microns. Our thickness, T1, is 1 micron. Our plate has a length of 250 micron. A thickness of 10 micron. And with regards to our capacitor, we're going to say that epsilon is epsilon naught, or 8.854 times 10 to the minus 12 farads per meter. And the distance between our plates is nominally 1 micron. Okay. All right, so we have an accelerometer, and it is experiencing an acceleration, which should cause some change in plate displacement, which should in turn cause some change in capacitance in our system. Okay. So how do we figure out what the plate displacement is caused by our acceleration? So we're going to have to take into account what we learned in our review section, talking about, you know, spring constants for guided beams and all that, this, that, and the other, and go from there. So anybody have any idea how we might calculate the spring constant of one of these guided beam springs? So the spring constant for a guided beam spring is 12 EI over the length cubed. Okay. So we have two different lengths here. Which one am I supposed to use? Yeah, the length of the spring should be fairly obvious, but I've seen some things. Okay. So we were given E. 12 is a number, so that's pretty straightforward. We know what L1 is. How do we calculate the moment of inertia I? So I, generally speaking, is AB cubed over 12, where B is the direction of bending and A is the transverse direction. So is our bending occurring in the width or in the thickness? In the thickness dimension, right? So it's going to be WT1 cubed over 12, and then we will plug that in. And in doing so, we'd find I is equal to 1.667 microns to the fourth. And so our spring constant for one of our guided beam springs comes out to be 0.166 newtons per meter. So what's our total spring constant for our system? Times 4, because there are 4 springs and they're all connected in parallel. So this comes out to be 0.666 newtons per meter. All right. So we have spring constant. We're trying to find displacement because the displacement of our plate should be equal to the displacement of our springs. So what's the piece that we're missing? So I'll just write it down out here. That's what Hooke's law tells us. F is equal to kx, right? Were we given a force? Acceleration. So I would argue that mass times acceleration will be equal to k times x. We just figured out what k is. We know what a is. We're trying to solve for x. What's left? The mass. How do we find the mass? Yeah. So the mass, if we neglect the mass of the springs here, which the spring should be much, much lesser in weight than the plate itself, is just going to be the volume of the plate. So that's going to be L2 squared times the thickness of the plate, which is T, times the density of silicon, which is going to come out to be 1.456 micrograms. From here, our plate displacement x will be MA over K total, or about 1/5 of a micron. We all okay with that? Anything seem too wild or crazy? All right, so our capacitance under no acceleration, which I'm going to call C naught, is going to be epsilon naught L2 squared. So that's just A divided by D, which comes out to be 553.387 femtofarads under the 10 G's of acceleration. This is going to look like epsilon naught L2 squared over D minus X, which comes out to be 704.554 femtofarads. And from this, we can say that our chain capacitance, which is going to be C minus C naught, is 151.167 femtofarads. So we have a change of 23.317%. Okay. Now, we can define some displacement sensitivity. And for an accelerometer like this, sensitivity, I would argue that this isn't a particularly good representation because we have a nonlinear relationship between capacitance and displacement, right? But we'll talk about other schemes that fix that later. We see that there's about a 0.705 picofarad per micron. So that is the change in capacitance per length of displacement, or, sorry, misspelled acceleration. Acceleration sensitivity of change in capacitance due to the acceleration. So this comes out to be about 15.117 femtofarads per G of acceleration experienced, where a G is 9.98 meters per second, excuse me, 9.81 meters per second squared. Okay. All right, so there's a couple. You have a question? So the A here is 10 times 9.81 meters per second squared. So it was taken into account in that calculation. Okay, so there's a couple of reasons why this is a pretty crappy accelerometer. Okay. First of which is we are neglecting any damping that's going to occur because we have a large plate there, but we could take care of that simply by fabricating small holes in it and all of that kind of good stuff. Another reason why this would be a particularly bad accelerometer, and we're not ready to talk about this too terribly much, our spring constant is actually kind of small here. And so if we were to bias this thing with an AC voltage, we would actually likely cause our plate to vibrate with that voltage as well, because our springs aren't stiff enough to really hold it effectively constant and only see the acceleration. Okay. One of the other reasons why this would be a bad scheme is because it only utilizes a single capacitance. Okay. So what I mean by that is it's the overwhelming majority of the time, it's usually better to take what's called a ratiometric measurement. Okay. So let me draw a simple picture of a bulk micro machined accelerometer to kind of explain what's going on there, right? So if we had a bulk micro machined accelerometer, so let's just say that we have large plate like so. And here we have sorry. Whenever whoever messed with my PowerPoints, they changed this drawing up significantly and it's messing with me, but I'll take care of it. So this is an oxide layer. This is an oxide layer. And this guy right here is effectively the area. Then we would have, so this is one silicon wafer layer effectively. And we're going to call this point in our circuit A. We would use an SOI wafer to make our actual movable plate structure, which I'm attempting to draw here. So this big block right here is a proof mass. And we have this SOI for this oxide layer connecting our mass to our plate. Stop erasing what I want to put in there. And then down on the bottom, we would have yet another thing. Need to make this shorter so it's not touching. My apologies. That's our big oxide layer there. So electrically speaking, and then this part right here is made from an SOI wafer. So electrically speaking, up here we have node A, and then we have some variable capacitance, which I'm going to call CW1. Here's node B. Then we have another variable capacitance, CW2, like so. And down here is node C. Okay. So effectively, as our proof mass travels up or down due to an acceleration, so let's say that our proof mass travels down. The capacitance seen between terminals A and B is going to decrease because the gap is getting larger, where the capacitance seen between terminals B and C is going to increase because the gap is getting smaller. So think of it like this. We have some plate here in the middle. Damn it. Some nominal distance D between both plates. But our plate is mounted to a spring. So as our spring extends in one direction or the other, we're making the D on one side get larger and the D on the opposite side get smaller. Okay. So this is a ratiometric sensing scheme. So if we wanted to determine the output of this thing, so let's say that we had some voltage V is equal to V naught cosine omega t here applied at the top. Here we have CW1. This is epsilon A over D plus X. Here's our output voltage. Here's CW2. And then we ground here. Let's say that CW2 is equal to epsilon A over D minus X. How can we figure out what the output voltage of a scheme like this is? Anybody remember how to do voltage division with capacitors? Of course not. All right. Okay, so voltage division with capacitors, Mr. Smartass. So let's say that we have a capacitor here. So just for the sake of argument, here's my voltage at the top. This capacitor Z1 is going to have an impedance of negative J over omega C1. Here is my impedance Z2, and it has negative J over omega C2. And then here's my output node, right? So using simple voltage division for impedances, we should see that V out is going to be whatever that voltage V is at the top node. And then we're going to have a ratio here, right? So it's going to be negative J over omega C2 divided by negative J over omega C1 minus J over omega C2. Or maybe it might be better to put negative J like so. Okay. So first thing that we can observe is that every one of these terms has a factor of negative J over omega in it that cancels out. So that would be V times 1 over C2 divided by 1 over C1 plus 1 over C2, like so. Now to make this math slightly less annoying, I'm going to multiply this by C1 over C1, this by C2 over C2, this by C1 over C1, so that I have a common factor of C1 times C2 in the denominator of everything, so that cancels that and that, leaving me with V times C1 over C1 plus C2. So the voltage drop over capacitor C2 is simply the ratio of C1 over C1 plus C2. Okay, so taking that into account, now that we know what the rules for voltage division are, let's apply them, okay? So that's going to be V times epsilon A over D plus X divided by epsilon A over D plus X plus epsilon A over D minus X. Everything has a common factor of epsilon A that we can throw away. So it's going to be V times 1 over D plus X divided by 1 over D plus X plus 1 over D minus X. And I'm going to do something pretty similar to what I just did a moment ago. I'm going to multiply this by d minus x over d minus x. I'm going to multiply this by d minus x over d minus x, and multiply this d plus x over d plus x. In doing this, I get rid of all of those denominators. And that's going to leave me with v times d minus x in my numerator, and then a d minus x plus d plus x, which looks like v times d minus x over d, or v times 1/2 minus x over d. And this is where the term displacement measurement is coming from, because we can see that the output voltage is proportional to the displacement x. Oh, you're correct, x over 2d, thank you. So this is what's called a single-ended ratiometric measurement, okay? Now, this is okay, nothing particularly bad about it per se, except that our output signal has a portion of the effective common mode signal in it. So by that, I mean our output signal has some DC portion that isn't telling us what's going on. So we could do something a little bit different, right? So double-ended ratiometric measurement uses a Wheatstone bridge configuration, okay? So if we put our voltage V at the top, and we had something like this, let's just call this C naught, C naught. This is going to be C naught plus delta C. This will be C naught minus delta C. There's ground. Let's call this V1. Let's call this V2. So effectively, we have two single-ended ratiometric measurement circuits, but they're in parallel with each other. And if we take the difference in the outputs, V2 minus V1 is only going to be proportional to the change in capacitance. Okay. So let's see what I mean here, right? So V2 is going to be whatever our voltage is V at the top, C naught plus delta C over C naught plus delta C plus C naught minus delta C. So that's going to look like V times C naught plus delta C divided by twice C naught, or we can call that V times 1/2 plus delta C over 2 C naught. Pretty much exactly what we got from our single-ended ratiometric thing a moment ago, but now we're just looking at a change in capacitance as opposed to a specific change in displacement. It works out the same way. What's V1 going to be, Stephen? C naught and C naught are the same thing. So what's V1 going to be? Half of V. Yes. Pardon?
Is it because I know?
No, it's because I like to pick on you because I know your head's been mechanical engineering oriented for the last 2 years, and so I like to tease you. He was a EE undergraduate student of mine, but he jumped ship like a, no, I'm not gonna say that. At least I'm not gonna record that. You are doing very well from everything that I've heard. I just like to pick on you, bud. So, If we take the difference of these two voltages though, we're going to see that the DC portion cancels each other out. And what we're left with is V times delta C over twice C naught. So we see that our output is directly proportional to our change in capacitance or directly proportional to the amount of displacement that our plate undergoes, right? So we have a simple linear relationship between output voltage and change in capacitance, right? So we get away from nonlinearity and all kinds of things like that. We have a simple scheme that tells us some amount of displacement gives us some amount of change in our output voltage. Okay, so this is where we are going to stop for today. I want to talk about capacitive comb drives when we get back from the break, and then also what happens if we introduce parasitic capacitances, because anytime we have two conductors with a voltage across them, they form a capacitance, and that is going to be problematic and can mess with our measurements. So, all righty, I hope you guys have a great and safe holiday break. I think I remembered to give you guys a little bit of leeway. I know that there are 4 homework assignments that are up at this point. I don't think any of them are due the day we get back, so that you don't have to worry about my crap for that. But I want to say homework set number 2 is due the Friday after we get back. And then number 3 is due the following Monday. And then number 4 is due the Wednesday after that. I'm going to try to get a homework set up based on what we've covered today. Probably 1 to 2 problems tops, just so I can kind of keep on track with that. But yeah, so anyway, have a good break. Don't stress out about this class too terribly much. I don't think it's worth your mental effort. And I'll see you guys when we get back.